For section 9.4, we're only going to concentrate on dealing with quadratic models. So far, we've done linear sequences and we've done geometric sequences. Now we're going to concentrate on quadratic sequences. So what I'm going to do is the example that's on page 678 in your textbook. It says to find a quadratic model. The sequence is 3, 5, 8, 12, 17, 23, etc., etc. Before I find a quadratic model, I'm going to confirm that it is a quadratic model. The way that I'm going to do that is to start by what sometimes is referred to as finding the first order differences. To get from 3 to 5 is plus 2, 5 to 8 is plus 3, 8 to 12 is plus 4, etc. If all of those numbers were the same, we would know that this sequence is linear, and then everything that we learned from section 9.2 applies. Okay, what we're going to do is extend that idea to find the second order differences. From 2 to 3 is a plus 1, from 3 to 4 is a plus 1, 4 to 5 is a plus 1, etc. So this sequence has what's known as a constant second order difference, where the difference of the differences is a constant. The approach that your textbook takes is to create a system of equations and then get the quadratic model that way. We're going to take a different approach. Recognizing that a sub 1 is 3, a sub 2 is 5, a sub 3 is 8, etc., etc., what we're going to do is pick 3 of those points. They can be any 3. It doesn't have to be the first 3. And we're going to correspond or get that information into our calculator in order to make the calculator do it as we want it to do. So if the first term is 3, we're going to put in 1, 3 as an ordered pair. 2, 5, 3, 8, etc. So after it gets in your calculator, it is going to look like that right there. Then we're going to go to Stat, Calc, choose Quad Reg. Our data is an L1, L2. We want to leave the frequency list blank. If you want, for the purposes of making predictions, you can store the regression equation, but it's not necessary for this particular question. Hit Calculate, and that gives us our quadratic model of best fit. Once we have that explicit equation, then whatever predictions we need to make, we can use it to make those predictions. All right, the next thing we're going to look at is a couple different variations of what can happen here. So this is number 74 from page 678 in your textbook. It gives us, I'm sorry, it's not 678, 680 in your textbook. It gives us a sub 0 is 7, a sub 1 is 6, and a sub 3 is 10. Two variations going on here. Number one, when you're dealing with sequences, you don't always start with a sub 1. Unless you're told otherwise, you can assume you begin with a sub 1. There are certain situations where it's better to start with an a sub 0 than an a sub 1. And we're going to explore that a little bit more when we do summation notation, which is going to be our next topic. So one of the variations here is we're calling our first term a sub 0 instead of a sub 1. Okay, second thing that's a variation from the problem above, we don't have consecutive terms. They're giving us the 0th term, the first term, and a third term. Just make sure that you get it in your calculator so that information corresponds. So the ordered pairs will be 0, 7, 1, 6, and 3, 10. Go through the same set of keystrokes we did up top, and that will give you your quadratic model. In this case, our quadratic model begins with n is 0 as opposed to n is 1. The top one, we automatically assume, because we weren't told otherwise, that we begin with 1. Here, we were specifically told that we're beginning with an a sub 0.